get a new surface actually more powerful.
I don't know if that was a surface issue.
I don't either. This is pretty good actually. It's an i7 chip and it's got plenty of memory and stuff. These are each one of these videos is about half a gig. So once you start doing things where there was a video being recorded in real time and you're doing MATLAB and this and that, start getting confused. Okay, so we'll wait our usual 5 minutes for everybody to show up. So let's just wait a couple more minutes for people to join in and move on. Turn camera off again. Okay, I think we can get started. So what we are doing in this chapter is system identification or dynamic system identification. To be precise, what the idea here is that you have a block which has an input and an output, and we want to see how this input affects the output. We are mainly interested in how the manipulated input here affects the controlled output, a control variable. And this is a very useful model because, again, it tells us what will happen if we take certain control action. Now, there may be other models that one may develop because, remember, we may have the manipulated input here, a manipulated variable that affects the output variable, which is my control variable. But there may be disturbances here, and these disturbances may be random. They may be the output of a block that is driven by random inputs, such as white noise. We have used that expression again and again for noise that contains almost all frequencies up to a certain upper limit, of course. People sometimes develop such models because if you have fast systems and the main disturbances are of this kind, it may pay to find how these disturbances affect the system. Namely, are they disturbances which have this shape, namely this question mark is essentially an identity matrix, and the disturbances are almost white noise that enter here? Or could it be that this is time? The disturbances are more like this, which means the white noise that drives this system may actually be filtered by a transfer function. You have seen this in detail, right? How filtering can happen. So if I have here a first order transfer function, for example, to be something like this, depending on where this tau is, I have here for log omega log amplitude ratio, all low frequency disturbances will go through. The logarithm is 0. And here I have the minus log tau, the frequency 1 over tau in the omega axis, beyond which we have disturbances that don't go through. This is the reason why this signal here contains a lot more low frequencies, these that go through, frequencies in this range, rather than frequencies in this range which do not go through, they get attenuated, right? We have seen all these concepts when we studied frequency response methods, and we don't have time to get into this or how one would build precise, specific models to be more precise or more accurate in describing these disturbances. And in fact, if one has such a model, there is an entire theory of how one would design a controller that would best counter these disturbances. This is sometimes called minimum variance control. So if this is known, you may do what is known as minimum variance control. And in fact, if a process is at steady state and you don't have any major upsets and load disturbances, and your disturbances are small random disturbances, then one can actually develop methods for controller performance monitoring. And I mention these things encyclopedically because obviously one can spend a lot more time on these techniques, which are for an even more advanced course. So these are automated techniques that check the controllers. Is my controller tuned well, or is my controller not tuned well? We'll see these things in a second, what happens when you try to build a model in the context of not accounting for this transfer function here. So this is again an overview of what we have focused on here with a small extension. We spent most of our time on this. And for this kind of situation, where mainly we want the manipulated variable effect on the output, if we have such a model, it's a good thing. I'll repeat it again, because if we have a closed loop system, such as this, then if this is the process P or C, and this is the set point, what is good for following set points is also good for rejecting disturbances. This D, again, wherever this D may come from, we always have that Y is PC over 1 plus PC times Y set point plus 1 over 1 plus PC times disturbance. And what is good for this, what makes this, the controller that makes this almost 1, also makes this approximate 0. So these two live together happily. Okay, what's good for the goose is good for the gander. Things are slightly different if we have the noise term, as we have already said. There we explain how we can use frequency response methods and so forth. So the only reason why you might want to go that route and be more precise and more specific about disturbances is when you want to make this approximately equal to 0. Well, even more approximately equal to 0, make it even smaller if those set point changes are not important and it's only disturbances that you have to reject. And you have an idea of what these random disturbances may be. But again, for most process operations, when you have load disturbances, what's good for this is good for this. The two live happily. The good servo control is good regulatory control. So the two live happily together, which is again why we want to see the effect of U on Y. This is the main thing that we want for our processes. This is why, again, process system identification is so important. A method that is popular for system identification is general linear regression. Give me an input sequence, give me a structure, and give me an output sequence. In fact, the input sequence will typically be in a computer control system, something like this. So this would be U, this would be Y. I'll do some regression, and I'll try to minimize essentially the distance. I'll write it a bit more abstractly between PU, if this is P, U is the input, minimize with respect to the parameters theta in P, minimize this so that you can get values for the parameters to be whatever. This is system identification. You can use general linear regression for this. And again, I'll repeat that the difficult part is mostly the structure. It's not so much parameter estimation. Estimation is easy for the most part, even nonlinear parameter estimation. Nonlinear regression works reasonably well these days. The more difficult part is when you don't know the structure, so you can calculate this distance well. We'll see this again. Of particular interest to system identification is the prediction error method. The prediction error method is almost like standard regression with a small caveat. What is the small caveat? It says if you measure this, the output at time k plus 1, and if you have a model that says this output is this function of the previous output and the input and the parameters theta, then use this measurement here and try to match this measurement on the left, this measurement here, with what this model predicts. Take all of these errors, square the errors, sum them up for all k, and minimize this with respect to theta. This will give you that parameter estimate. We've done already a number of calculations, and we said the basic idea is simple. In fact, the reason why this method has been so incredibly popular is that when it was invented, computers were not so powerful and calculations were difficult. And this method for linear models, for example, when this thing here, for example, is a linear model of the form, let's say, AYK plus BUK, then minimizing this minus that, the error squared, the sum, minimize with respect to the parameters A and B, A prime, B prime. This is easy because it's linear regression. So I can write it down explicitly. I can even do some statistics with a little bit of abuse of the notation of the theory. So I'll remind you rather, that if you have things like y1 through yp or y2 through p plus 1, the actual indices don't matter. These are your measurements. These are your model predictions, A prime, B prime, and this is y0, u0, yp minus 1, up minus 1. In the previous lecture, we had this 2 to p plus 1, 1 through p. It doesn't matter. Again, these are just indices that show the shifts. So if you have this, again, these are measured. Therefore, they are noisy. This is column on the right. This column is assumed to be known exactly, but this one on the left is not so. So this is noisy, as is this one. Nevertheless, the method works quite well, so we can apply the standard regression techniques that say if this is my vector y and this is my matrix x and this is my parameters theta prime, then from this I get my theta hat to satisfy x transpose x. Theta hat is equal to x transpose y, and we call this the information matrix. And we can, if noise is small and this is almost well known, then you can get a decent estimate of the variance of the parameter estimator as sigma square noise x transpose x inverse. There are other terms here for this equation here, but I don't want to bore you with that. The two textbooks I mentioned, either by Leung or by Soderstrom and Stoica. This one is now free on the internet. They describe those things very well. There's a smorgasbord of formulas there. I don't want to bore you or confuse you rather with too much stuff. If you ever need the ultimate in the sophistication of these things, you'll extend these ideas. It's the basic ideas that matter. Basic ideas are standard linear regression. Now, we said we're going to discuss today about what could go wrong with these things. What could go wrong is associated with two things. One is that this F here may not be a very good choice for what we have. In fact, this whole regression problem may not be a good option in the form we have it here as least squares if the disturbances happen to be far from what we assume, far from the randomness we assume. We'll explain this. The other part is this. Well, if the information matrix is not well formed, then we'll run into trouble because the variance, the spread of our estimates is going to be enormous if the inverse of this matrix is not very well known. If this matrix is not well conditioned, if the experimental data is not good, we may not even be able to invert this matrix. So we'll see all those things in terms of examples. That's the easiest way to explain what could go wrong here. So let's get started. After this lengthy introduction, we are now ready to see some action. We're going to see again things that go right and things that go wrong in the prediction error method. Example 11. We are on page 34 of the notes. Example 11 rather, on page 34, which is based on example 7, has the standard linear model yk plus 1 is equal to ayk plus buk plus wk plus 1. This is what we call white noise. So what is white noise? It's W as a function of K. At each point in time, these points here are completely random, and there is no way, there is no model to predict the next value, say this one, by processing the previous value. They are not related at all, okay? That's why this noise is called white noise. It's called noise because it's random, and white because there is no correlation whatsoever. So the expected value between, let's say, WK and WL, or better yet, K plus any other number, let's call it K0. If you take any two points that differ by K0, for any K0, this expected value is 0. And this is the correlation function because the expected value of for all K0. The expected value for all noise signals is equal to 0. This is 0 mean. zero average. Okay, so this white noise goes above and below zero randomly. How far above or how far below is completely random. And in fact, this is a sequence that follows the IID property. It's an independent, again, they are not correlated at all, so they're completely independent, in fact. Independent and identically distributed. All of these points follow the exact same distribution. And that's the assumption here for this white noise. Based on this, if we assume here that in addition to this being any noise, the identical distribution here is Gaussian, so normal, the normal distribution. So we are going to do a numerical experiment for which the values of A and B are known. So A has the value of 0.8 and B is equal to 1. That's what we use to generate our simulated data. We're going to make a step change on the input, pretending we do a step response experiment. So these points are going to be here. 0, 1, 2, 1, 2, 3, etc., etc., etc. And we observe the output. So how are you going to do this identification? I have already mentioned this. After 1,000 times steps, after we do this experiment, so this goes to 1,000, right? We have lots of steps here. And we record Y. So Y starts from 0, it starts from steady state. Everything is ideal, and it goes, it's the same time scale, and it goes like this. But there is noise. The noise we use in this simulation, I mention it in the notes. I believe it's I'll find it out. So we do this experiment, we have lots of data. In reality, as I already started saying, the experiment looks like this. So let's copy this so we can understand what's going on. So this is our example. Oops. Page. This one here. Did I start with the wrong example? So this is example 11. Yeah, that's my example 11. This is what we're doing. So we are looking at the estimates in this experiment. Let me copy these data to my box. Oops. Let's try to understand what we see here before we do much. So what do we see here? We see a step response experiment. So initially, our input was at 0 and it goes to 3. We make a step equal to 3 and it stays at 3. Now, the output, if you observe, it follows a fairly noisy output. This is a very noisy system. And the output actually starts from 0. Okay? Now, the reason why I do this unrealistically long experiment is because I want to make a point. I want to make a case for what's going on here. With this experiment, we have lots and lots of points, and you see that for quite some time, we cannot identify the parameters well. You see that we have here about a couple of hundred of time steps, and nothing's happening. Incidentally, the code for that I'm giving you in the notes, so you can run those things on your own in MATLAB. Change parameters, do anything you want. Okay. So first observation is that because this is noisy, for the first several time steps, if you do regression, you don't get good values. The actual values of the parameters are 0.8 and 1. You see that you get something like, like this here. Well, the parameter B is approximated with something well above 1. It's close to 2, what is? And A hat, maybe a little better. Okay, maybe A is estimated a little better. Okay? That's one observation. What other observations can we make? Well, if you look at what you get here at 1,000 time steps, you get A hat and B hat to be equal to 0.8160. And I'm just going to report this with 4 significant digits, even though there is no notion that I know this with 4 significant digits, right? 0.8720. So for this system, the true value of A is 0.8. I know I'm estimating this as 0.816. That's decent, one would say, correct? Why do I say this is decent? It's just by arbitrarily judging the 0.016 to be not too much in terms of, by comparing it to 0.8. Okay, the error is about 2%, 3%, something like that, right? And I consider this reasonable. There are other ways to judge this, especially if you're close to 1, in which case, if you estimate something at 0.97, for example, your A, you'd say this is below 1. If this is my A, the system is stable. Could it be that A is 1.01 and my system is unstable, drifting away from steady state? This is more important. Nevertheless, this is nice, clean, stable. B is known with higher error, therefore, this is not as well known as this A. However, what is also very interesting is that from this exercise, you can actually get one parameter of your system quite well. Even though we say that A and B are the 2 parameters, we can write the system also in continuous time or in discrete time in terms of the gain and the time constant. And the steady state gain of the system is easy to find. Let's do it from scratch without transfer functions or anything like that. Very easy. Yk plus 1 is Ayk plus Buk, right? When I make a step change M to Uk, eventually my system is going to reach Y infinity equals Y infinity plus Bm, right? My output is going to go like this, Yk versus k. It's going to reach that value here, which is my Y infinity. And what is this Y infinity as a function of M? This is my steady state gain, Let me calculate that in terms of A and B. Help me with the algebra. So Y infinity, this implies Y infinity is equal to, in terms of B and A, just first order algebraic equation. B over 1 minus A, yes. Okay, this is my steady state gain, K. So let's see what is the real steady state gain from here. I have the real steady state gain, the real, because I'm creating simulation data, is equal to B over 1 minus A, which is 1 over 1 minus 0.8, which is how much? 5. Let's see what is the estimated steady state gain. So that says the estimated steady state gain is B hat 1 minus A hat, which is equal to 0.8720, 1 minus 0.8160, which is 4.7. So let's try to assess here relative errors. The true value of B is 0.8. There is an error of 0.07. It's of the order of about 10%, I would say, right? The A error is small. The steady state gain error is also small. It's 0.3 out of 5. So in fact, theory can tell you that this experiment can actually estimate this gain here reasonably well. There is a technical term for this property of this experiment, which is captured by the following. This input, a step, has the persistent excitation property for steady state gain estimation. What is persistent excitation? Persistent excitation is a property of process inputs, which does that. It persists in exciting the process. Why is this a good thing? Because if you don't excite the process persistently and you just stay idle, essentially here, let me highlight this, the process doesn't tell you much about it, about its dynamics, right? You excited the process once, and as you went in this direction, well, after some time, you lost all the excitation of the dynamic, or the dynamics of the process. Essentially, the process now sitting at a new steady state, you don't see much. The only thing that you can tell well qualitatively is at what new value this process settles, because you can average that and can get that pretty well. This is the reason why this persistent excitation property is satisfied by a step. If you want to get the dynamics of the process well, here we got lucky with A hat and got it real well. If you have more interesting dynamics, you need more excitation. And signals that have better persistent excitation properties are signals that have more ups and downs. So instead of having this constant step at 3 here all throughout, all the way here, you can have a signal that is up, down, actually, all the way. This starts at 2 here. So if I may just take that. So a signal that is more like this, randomly up, down, up, down. This is exactly what example 10 looks at. We'll go to example 10, but before we go to this, to that example, let's also do one more thing. Here, we assumed that this, the effect of this white noise is captured by this model here, right? So is it true that in the very beginning, when I said here, I have the manipulated variable, the control variable, and I have a disturbance here, which I captured like this. Is it true that this transfer function here is 1, and what hits my output is pure white noise or is it filtered noise? Well, let's check. So I can go from this, I'll repeat it so you can follow it. So this is my model structure. And I'm asking the following question. Is it true that when I have U and I get Y and I have here a disturbance driven by white noise, is this block equal to 1 or is it something else? Okay, let's check that. If it's 1, this is what goes here is just pure white noise. If it's something else, it's practically something filtered. Okay, so it's smoother noise. Well, let's check. We can take Z transforms. Z transforms say Z times Y of Z, forget about initial conditions, is equal to A of Z plus B U of Z plus W of Z. And now I can solve for Y of Z, so I can get my transfer functions. I get that Y of Z is something U of Z plus something W of Z. Help me with these two somethings. What is the first fraction? So this fraction is what again? Well, I need to solve this algebraic equation for Y of Z, first order algebraic equation. Numerator is what? For the effect of U?
B over Z minus A,
Excellent. And what about W?
just 1 over B minus A, Z minus A.
Yeah, very simple, right? And these are both first order transfer functions. So I know that first order transfer functions do some high frequency filtering, which basically says that the effect of white noise here is going to be filtered by this first order process. It's in discrete time, so let me say a bit more about frequency response in discrete time. In continuous time, we said if you have P of S, essentially you need to get for frequency response P of J omega. Let me finish this and I'll let you ask your question. So when you have a corresponding discrete time transfer function, frequency response is by G e to the J omega. Okay? So you replace, here you replace S by J omega, here you replace Z by e to the J omega. And when you do this for a first order system, so this is, say, K over tau S plus 1, we have log omega, log amplitude ratio. We have this filtering at low frequencies that go through and high frequencies do not go through. It's the same when you do it for discrete time transfer functions to see what this looks like. It looks like this. It's only that this makes sense only up to frequencies that are pi over t. T is the sampling period. Okay, that's a discrepancy between continuous and discrete time because frequencies above that don't make sense. They have to do with aliasing. There was a question. When we took the Z transform of this? Oh, this one should. Okay. Yeah. So there's an extra Z here. Correct. Yeah. Good catch. So all of this is, again, understood to be relevant to identification. The important thing remains that this is the more important transfer function. This is sometimes useful for all practical purposes, particularly when you use the prediction error method. Assuming this to be white noise makes your life easier. If it's anything else, you may use more sophisticated methods. We'll see actually in a second when this makes a difference. Okay. So I'll close this discussion for this example, and I'll continue with what we started saying, which was, again, this experiment is okay. Step response experiment is good. In fact, it's optimal for estimating steady state gains. A step has the property of persistent excitation for estimating the steady state gain of the process. Such an input, though, is not optimal for estimating all the dynamics of a model. There is beautiful and powerful math that can help you prove this, but I prefer to resort to intuition now to explain this, as I did a moment ago. Namely, if you just use a step, you can see very well what is the steady state gain, because the steady state gain is essentially this value divided by this value here, right? And this value you can estimate well by just averaging the long-term value of y. It has settled already very quickly. So that steady state gain you can get well. The dynamics, it's only this little tiny piece of initial data, so you may not get it very well. A better signal is this. A physical example I've mentioned a few times is estimating the dynamics of a car. You can turn the wheel once and you find how the car turns in that single turn of the wheel, or you can keep turning the wheel left and right, left and right, left and right, in which case you're going to find out more about the behavior of your car. And in fact, you don't turn the wheel periodically with the exact same period. You turn a little bit to the right and then a lot to the left, and for a long time to the right, and short to the left, and medium to the right, and so forth. This is the PRBS signal here. Remind me again what PRBS stands for. We mentioned it last time. Somebody, you don't have to remember it, you can look it up. Just look it up. Very good. So a pseudo-random binary sequence is better. This is what example 10 tries to do. You have a pseudo-random binary sequence, which is optimal, and you use that pseudo-random binary sequence in an effort to estimate the parameters of a model that is first-order model, and you try to do your job. The only thing is that the noise model now that perturbs that system is not the white noise you assume, but something else. So let's go to example 10 on page 30. Example 10, again, uses a PRBS sequence, something like this. And it looks at the output and tries to estimate this model. The model structure is this. That's what you assume. But the true model, well, true in the simulation, right? So the true structure here is slightly different. It's here WK plus 1 plus C, a third parameter, WK. Both of these are white noise. The only thing is that now, because you have this kind of essentially averaging between two successive values, this signal already is going to be smoothed out somewhat, because you average essentially between two values, depending on the value of C, of course. And if you do your identification, you're going to do your usual thing, right? You're going to say, this is my parameters. I'll just follow the notes. Usual thing, you have y plus 1 minus your model A, B, this, which is y, u, all the way down yp, up. This is your x, this is your theta, this is your y, from which you get that theta hat is the solution of x transpose x. Theta hat is x transpose y. Great. The only thing now is that all this is valid, assuming that it's the optimal estimate here. This theta hat is the optimal estimate when this W is white noise, but now it's something else. So we never actually accounted for that. So depending on the value of C, which here in the simulations we chose to be C, we chose to be 0.8. This is the true value. Okay. Notice that C doesn't appear anywhere here. I'm not building anything. My method does not know C. As I explained, there are methods that allow you to estimate C by doing nothing to the process. You just observe the noisy output and you can fit such a model. This is more advanced. I don't want to take any time because it will distract us. So let's move on to just explain what goes on here. So when we collect these data, we'll see something like this. So I'll have to copy this. Again, this is, along with the MATLAB code, the outcome of this simulation. Now notice that there is no problem with the kind of experiment that we do. The experiment uses very good input data. In fact, it uses the optimal input according to theory, which is random PRBS signal. So this is presumed to excite the process well. By exciting the process well, I ensure that this matrix is going to be a good matrix to invert it. It's going to be well conditioned, and I'm going to get hopefully good results. But what I see here is that the outcome that I get is not very good. Why do I say that the outcome is not very good? Well, let's look at B. What is the true value of B? A is well, the true values. True values are 0.8 and 1. If you look at this here, this is reasonable, but this, what does that look for B? This is 0, this is 2. So what is the estimate for B roughly? You can eyeball it. 1 point something, right? 1.4, 1.5 maybe, something like that, right? So it's 40% off from its true value. So this is B hat. The reason why I have this issue here, and you see that the method is stuck there, it's going to give you a biased estimate no matter what. It's not that you didn't have enough data. In fact, the excitation was pretty good. You converged reasonably quickly. It's 100. This is not 1,000 data points. It's 100 data points. Far fewer data points than before. Up here we had 1,000 data points. Right? Here we have 100. With 100 data points, very quickly we converge to something reasonable. Unfortunately, just because there is a different noise model that perturbs our process in a different way, we are a little bit off. Nevertheless, of course, you see the good property of exciting the process most of the time. We don't excite it just once with a step to do something like this, where we do something here in the beginning, and then for the rest of the time, the process would be asleep. Here we keep the process awake all the time, up, down, up, down, up, down, up, down. And we see it behave dynamically all the time, which is why we converge very quickly. In 20 time steps again, look at this here. We need about 200 time steps to converge to something, okay? Which is the reason why in industry now people do use these things. people do use these inputs. Those implementing those signals before computers became so widespread, it was a bit of a tedious process. You had to do it manually, or you had to babysit your system. Now it's done automatically, particularly for multivariable systems. This technology has been around actually for a couple of decades at least. I don't want to advertise companies, but also I'll just say it verbally, orally. So Aspen, for example, has the open step technology, which automatically can do this kind of excitation of a process. Honeywell also has this capability to excite the process automatically. Most other companies have this option to excite your process, so you can see this. So the issue here is, yes, we're using a good input signal. If all of our assumptions are good, we would get a good set of parameter estimates. Unfortunately, here the model, the noise that we have is not correct. That's why we get this bias here in the estimate of B hat of B. Okay, so we get biases. Let's move on to more examples to see what could go right and what could go wrong. So here in example 12, page 37, I'm doing something which would be patently unwise. Namely, I do a pulse response experiment. Why? Because we know about finite impulse response models, right? And somebody says, well, if I use a finite impulse response model, and this is in continuous time, in discrete, actually, it should be finite pulse response model, but people use FIR for everything, so we'll stick to that. Same model structure, same everything, except now our input U is just a pulse. So 0, 1, 2, 3, K, U sub K. So what happens to Y? Well, it jumps a little bit here, and then it has to go down again and just be noisy and give you these things. Obviously, here you excite the process just a tiny bit, and you don't see much of it. That's why if you collect data, or even if you collect a lot of data, you get very poor estimates. Let me convince you about that by showing you a simulation. So if we go here, I repeat everything here for completeness in the nodes, and not for this one, as for the next one with the pulse here. So for the pulse, okay. So for this, I'll take it to my main notes. What I see is that essentially it's only this tiny point that excites the process. For the rest of the time, even though I have 1,000 data points, they are of no use. Because during all this time, the process has been sitting asleep. Right? It's only this tiny little blimp that matters, which gives me horrible parameter estimates. You see that? We get point something here, maybe 0.8, 0.9 for A, and B is close to 2, I guess. They make 100% error. One would never ever do this kind of experiment, so I want to emphasize once more that even though we have finite impulse response models, and let me remind you, those models actually have a particular structure which can be general, so it's sigma of H I U K minus I. I goes from 1 to n. So these coefficients are the actual values of the output when this is a pulse. So this is to define the model. We never do that experiment. We still do experiments the standard way, having PRBS signals. We want to excite the process most of the time, so we can see how the process behaves dynamically. We don't want to keep the process asleep most of the time, as we do here. Here is another situation. Example 13. Example 13 actually may happen frequently because it's always a um, very valuable wishful thinking for many processes to try to build a model from ordinary closed-loop data. Why is that? Let's try to put some context. So you have your process. Let's say it's a CSDR, or let's say it's a packed bed reactor. It's whatever you have there running in your process. And you build a controller for that process based on a model you identified after doing laborious experiments. You design, tune the controller works well, great. After some time, the process will change for a number of reasons. If it's a reactor, the catalyst slowly deactivates. If it's a heat exchanger, it may foul and you need to clean it up after some time. There are all kinds of changes that happen. So here is your supervisor. You're a young process engineer. Your supervisor comes to you and says, here are some data. Here is this big Excel sheet that contains lots of operating data from recent operation of my process. Can you build a model so that we can tell how different that model is from what we assumed at the beginning of this exercise when we built the controller, say, a couple of years ago? And we want to tell whether these two models are very different. Okay? This can be done once in this context, or people may actually automate that process and say, I'll have a fault detection system. Fault detection and diagnosis, I'll write this term because it's very important. It's a process of, it's a capability rather, of great significance in practice, because for safety purposes, you may want to identify things that may be dangerous. In fact, you want to predict when something dangerous happens, and it doesn't have to be a serious fault. It can be something like my controller is okay, but not close to optimal. It doesn't give me very good performance. And I would like to detect. What does detection mean? It means to tell that something is wrong. And what diagnosis mean? It means I can tell what the fault is due to. So here I find what is going wrong? Okay. Well, what is the status of my process? And here I find why. Why is this happening? What is who is the culprit for this? What is the source? So what may be, well, my catalyst is deactivated. Diagnosis, well, there have been carbon deposits on it, substantial, so I need to take it out and put a new catalyst for my process, okay? For this, estimating a model from normal operating data is always very desirable. Unfortunately, when a process is under control, it makes it hard for you to tell how the process is behaving, because the controller is related, takes action, and its output is related to the output of the process, which it may have significant effects. Let's say this through example 13, which refers to the following situation. You have a process, but around that process, you have built a P controller. So I have my process. So I have yk plus 1 is ayk plus bek. That's my model. And around that process, I built a P controller. So my controller has just a gain. Okay. So here I may have disturbances. I have the output. I have the set point, the error, the input. And I'm collecting my data and I'm trying to apply regression. so that I can estimate A and B. Let's do this together. So to apply regression, I'll take y2 through yp plus 1. I have my model, A prime, B prime. This is y1, q1, all the way to p. And this is my matrix X. This is my parameter vector theta. This is the error. This is Y. And this implies that A hat B hat is the solution of X transpose X. A hat B hat is equal to X transpose 1. Okay, simple. And the same thing as always, which is why in the notes, I keep repeating this ad nauseum. It's the same procedure, exact same procedure. But now we have a different problem. What is the problem? Well, when we try to solve this system of equations, there is a problem with this matrix. Let's try to understand why. Because the system has been working in closed loop and nobody changed this set point, so this set point has been staying at zero in deviation form, meaning at its nominal value. So we have that the input u is related how to the measurement yk at all times? Well, it's the controller gain times the error, which is y set point at time k minus yk. This is the error at time k. This y set point is 0, so this is minus k yk. Right? All right. Now, if I take then this matrix X and take this into account, it's immediately obvious that this matrix has a problem because it's this matrix of data. And this matrix now, this matrix X is, well, let me ask, what is the rank of this matrix? What is the rank of a matrix? If I have a matrix, it has columns and rows. The rank of the matrix is the maximum number of linearly independent rows. This is the row rank or the linearly independent columns. This is the column rank, and you can show by a theorem that these are equal, and this is therefore called the number of linearly independent rows and the number of linearly independent columns which are equal. This is called the rank of the matrix M. So if I have the matrix X here, well, what is the maximum number of linearly independent rows or columns? Look at columns, which are easy. There are only 2. How many are linearly independent? This matrix has 2 columns. At most, it could have 2 linearly independent columns. Are these 2 columns linearly independent? A, C, exactly. Are these 2 columns linearly independent? No. Why? Well, the first column, let me write it as analytical as I can. The first column is y1, yp. Can I write the second column in terms of the first column and multiply it by something? So this is the first column. What do I have to add so I can get the second column? Get this. Say it again? Yeah, minus kc. Okay, so if I multiply the first column by minus kc, I get the second column. So are these two columns linearly independent? No, okay, one is a multiple of the other. Okay, so these columns are not linearly independent. Therefore, the rank of this matrix is not 2, it's 1. And that's why you can show immediately that X transpose X has rank 1. It's a matrix that is not invertible. It's a singular matrix. Let's convince ourselves, because this is a very simple matrix. So let's construct X transpose X. X transpose X is equal to, help me write X transpose in terms of X. X is up here. And this is going to be X. So help me with X transpose. The first row is what? Through YP, excellent. And the second row is minus KCY1 all the way to minus KCYP. Good, and this is Y1 YP, and this is minus KCY1 minus KCYP. And let's do the multiplication again. Quick reminder, rows and columns in the first and second matrix, and the multiplication is going to give me a matrix of what dimensions? The first will go first, and the last dimension will go last. So it's going to be 2 by 2, right? Let's write the first entry here. What is the first entry? It's going to be this multiplied by this. Help me do the multiplication. It's going to be this multiplied by this, plus this multiplied by that, plus this multiplied by that. So this is going to be the sum of what? The first is y1 times y1 squared. Then y2 times y2 squared. yp times yp squared. So this is the sum of what? Yeah, yk squared, right? And what about the second? Well, let's go down here. In this block here. What is this block here? The sum of what? Now we multiply, let me do it by another color. This. So again, now I multiply this by this. So help me with that summation. What again? Minus KC. Yeah, this, right? Fairly straightforward. And what about the off-diagonal elements? For example, this is, let's do it another color, this. So I have to multiply this by this, so I can get this element here. Help me with this. What is this? So fix the typo here. There is the minus becomes plus, and there was a square that I forgot. Let's do the green ones. The green multiplication, sum of. Say it again. It's this multiplied by this, and going. This multiplied by that. So minus KC comes out. And what is left inside? Yeah, YK squared. And it's the same thing here because of symmetry. So this matrix then is a 2 by 2 matrix. It has, let me write this to be complete, minus KC sigma YK squared. Does anything come out as a common factor? Yes, sum of yk squared. And what is going to be left inside? 1 minus kc, yes. Minus kc because of symmetry, and kc squared with a plus. So that matrix X transpose X then is this matrix. What is the determinant of this matrix? This minus that. Well, yeah, this is a constant, so we can leave out the constants. The determinant of this matrix is this quantity minus this quantity. So it's this square, which is a constant. We can leave it out. This minus that is what? 0. Yeah. So this is not a good matrix. You cannot invert it. So let me summarize. What did we do with this exercise again? All this algebra. We now have a system that is under a closed loop control. We get some normal operating data. And from these normal ordinary operating data, we try to estimate a model. But unfortunately, the controller is such that when we try to apply the prediction error method, the matrix X that we get, which appears here in the estimation, unfortunately, the matrix X is such that X transpose X is singular. So this we cannot solve. We cannot go anywhere with this. We lost complete sense of identifiability here using the prediction error method. Now, this is an extreme case, of course, that has become famous because it appeared in literature many years ago, and it alerted people that closed loop identification is difficult. So one then might say, all right, so if my process is operating under closed loop control, am I completely doomed? Well, you can do a few things, but you have to have a scenario different from this. Okay? Somehow, you have to destroy what created this unfortunate situation. So you have to do something. That discussion of what you do to get around the problem of closed loop identification. So this is closed loop identification, or closed loop IED for short. It's a perennially favorite topic in research because closed loop ID has all kinds of difficulties that come from the fact that the input U to the process and the output Y are seriously correlated because of the feedback path. So they don't, this messes up things in a certain way. In fact, again, as the discussion on page 43 indicates in this problem, if you have your process G and your controller C, and you have disturbances here, and you have noise, and you have your feedback path, and you have your Y set point here, the error, the manipulated input. I left input disturbances, sensor dynamics, actuator dynamics, I left all these out. The general identification problem says, if you measure Y, and so measure, and you know U from the controller, from your controller, then if you have a certain model, G, so G, think of this as a general mapping, then G acting on U should produce Y. Subtracting one from the other is the error. A norm of that error tells you how large the error is. You try to minimize this by selecting G. That's a general closed loop identification problem in a somewhat abstract way. The problem is now that U, because of this controller, is the controller times Y set point minus Y. So it's this U that you have to stick here. And therefore, this problem is essentially, if you put this, you get minimize with respect to G, the distance between G, C, Y set point minus Y minus Y. And this is a problem, it's a difficult problem. You cannot solve this in general. Okay? Find G so that you can minimize this. And now this is measured. All right. Now, if your set point doesn't change, things become a little simpler. If your y set point is equal to 0, then the above minimization problem becomes minimize with respect to G times C times minus y. And if you assume that your controller is linear and the system G may be non-linear, but this can be written as minus GC times y, although you don't need that. Let's keep it general. So this is, I have minus y here, minus y there. So this is equal to, let's keep it general, GC plus identity, or 1, let's just keep it as 1, acting on minus y, minimize this with respect to G, but this minimization is trivial. This implies that G optimal is the optimal G is the G that makes GC equal to what? So it can make this the smallest possible value. Remember, this is a magnitude, so this is always greater than equal to 0, right? It's a norm of something. So the smallest value that this expression can take is 0. Well, there is a trivial value for G, a trivial model G that makes this 0. Which one is that? It's the one that makes GC equal to what? Minus 1, yeah. Which means G hat is minus C inverse. This is worthless. This has no new information. It tells me that the best model is minus the controller inverted. Well, the controller just built it. There is nothing new here. This realization has been around for quite some time, and all methods that do closed loop identification find clever techniques to get around this problem. So somehow this sequence of logical steps has to be destroyed. You have to find something that prevents you from following so that you won't go here. You don't want to end up here. Okay? This is not good. Somehow you need to cut this chain. Well, there are a number of ways to do that. One way is to prevent this. So prevent this. You can have closed loop identification where you change the set point now. Make PRBS changes on the set point. This will prevent you from going that route. That means you have a way to actually get something. That's one trick. People do this in practice, actually. A lot of closed loop identification takes place in industry. People will change the set point by a reasonable amount. They'll get an updated model. There is a penalty because your output is not exactly at the desired optimal set point, but it's the best you can do. You cannot do much. Another thing is to cut it here to prevent this from existing. So, or prevent this equality. And this is basically saying that prevent this from existing. So make C non-invertible. Well, that's what the self-tuning regulator does, actually, if you think about it. Think about it. What is a self-tuning regulator? You have your process, P or G, let's say G. You have your self-tuning regulator here, which is a block that has this step function. If the error is positive, this input goes to its maximum value. If the error is negative, the input goes to its minimum value. This function is not invertible. If I know E, I can tell U, but if I know U, I don't know E, right? U could be here, here, this value, this value, this value, this value, this value. I don't know what E is, right? E could be this, 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 this. they all correspond to a U value equal to its maximum here. And if you have U at its minimum, could be this. All of these error would result in the same U. So for this, the inverse does not exist, the inverse of the controller in this closed loop. And that's why the self-tuning regulator actually works. There is no external excitation, no nothing. It's just small disturbances and noise that drive everything. And you can tune controllers nicely. Also, the Ziegler-Nichols method is a method that makes, well, let's see, the continuous cycling method. The continuous cycling method by Ziegler-Nichols uses a P controller, right? And yet, from that, we can tune a controller. How does it do it? We just said if you have a P controller, you cannot identify anything. How does Ziegler-Nichols do it? The continuous cycling method. Well, the trick is that this gain, let me use another color. The trick for Ziegler-Nichols is that this gain here is not constant. We change it, right? We change it so that we can bring the output to continuous cycling. So because this is time varying, there is no way for the inverse to be equal to the process because the process is time invariant. So you prevent C, the process G to being equal to minus C inverse. Okay. All of these things are discussed on page 43, and I have some specific examples where actually we use all of these ideas. Let's take a moment to go over that and we'll close this. So example, I'll just show you the results of all of these ideas. So this is my discussion and these are the examples. So this is an example where I change the set point now and everything else remains the same. The process is under closed loop control. And let's copy this. So, okay, oops. So I can. So in this example, the set point changes, the input to the process now is a nice, persistently exciting signal. The output changes. And by the way, you notice that if you just look at these data, you would say, I see no model, I see nothing, right? And yet, if you see the parameter estimates, well, you get something. You get some estimates that, well, they may be somewhat biased, but you converge to some value. It's nowhere near perfect because you have to adjust a number of things, but it's okay in terms of recovering identifiability. Remember, with the P controller, we lost all identifiability when we didn't excite the process externally. Another way to do that is by dithering the input to the process. In this case, you add an excitation signal to the process input. So the controllers suggest something, you dither that. Dithering comes from electrical engineering jargon. And in this example, you have the controller that provides feedback, but you add the signal D, a small dithering signal, which I'm showing here. With this one, this is the dithering signal here that you add to the output of the controller to the process. So what goes to the process is the dithered signal that is here. And you see that the actual input, again, is nicely, persistently exciting. Well, you get something here. You recover identifiability. You didn't lose all identifiability in this case, even though you have closed loop control. And finally, well, you have the case of a time varying gain. And you have to play a little bit with that. But here is a feedback control system where the gain changes. So this the gain to the process changes as a result. You recover identifiability. You see the gain now goes from, what is it, 0.1 to 0.5. How did I know these values to be good? Well, by simple analysis, stability of the closed loop. Okay, just doing a reasonable analysis. You see that the process input has enough excitation, the output has enough excitation. You recover something. You get the parameter values that you wanted to identify. I have the code and everything in the notes if you want to play by adjusting parameters, changing things around and all that. So this works well. And of course, to convince you that the relay feedback actually works, I have just a typical example for the self-tuning regulator with hysteresis. When you go in this direction, you have to go a little bit higher than 0 to switch to this value. When you go down, you have to go below this, go like that. And this is what the self-tuning regulator does. And indeed, it gives you pretty good results for identifiability, even though you have feedback control. And again, this is because your feedback controller is not invertible. This gives you identifiability. Your controller cannot be equal to inverse. The process cannot be minus inverse the controller because the controller is not invertible. So you avoid this trap. Okay. So this concludes this chapter on identifiability and process identification in general. We barely scratched the surface of this topic, which is very important. I prefer to go breadth first rather than the depth first. So there are countless results on when the method converges, the prediction error method converges, when it is biased, unbiased, how much is the bias, what confidence intervals you can get, what confidence on predictions you can get, and all these things. Those are for an entire course to cover these things in detail. But I prefer to show you when this works and when it does not work, and combine this with a little bit of intuition about what happens in a closed or open loop during identification. With that, we'll close this. Next time, we're going to start multivariable systems. It's a new PDF. I already have it in on Canvas, so you can take a look if you care. I'm still making refinements and corrections, so it's not free of bugs and typos. So you're welcome to take a look at it. But for next time, for our next lecture, there will definitely be a slightly different document where I need to fix several bugs and typos and all that document, so we can have a nice clean version. But you can look at it, it's already pretty good if you want to early look at this and get a sense for what we will cover next. Okay, so until next week, I'll see you all then.